Unveiling the intricacies of convolutional neural networks, convolution and pooling. Good afternoon, scholars. Today, we're diving headfirst into the depths of convolutional neural networks, or CNNs. You'll leave this lecture with a deep understanding of the roles of convolution and pooling in these powerful deep learning models. Convolutional neural networks, CNNs, are a class of deep learning models prominent in image analysis tasks. They are designed to automatically and adaptively learn spatial hierarchies of features from mountains of image data. In CNNs, convolution refers to a specific mathematical operation applied to the input data using a filter or kernel. Convolution is a mathematical operation on two functions that generates a third. In the context of an image, this process expresses how the shape of one image is modified by another. The convolutional layer's purpose is to detect features like edges, colors, gradients, and textures within an image. Each filter in a convolutional layer learns unique characteristics from input data. Stacking these layers enables CNNs to discern complex patterns. We must specify some parameters when handling convolution layers, such as the number of filters, filter size, and network architecture. Note, convolutional layers have fewer parameters than fully connected layers, making them an asset in building deep networks. In convolution, stride length refers to our step size when moving the kernel across the input matrix. This stride influences our output feature map dimensions. A smaller stride results in larger output dimensions. Padding involves adding extra pixels around the input matrix to control the spatial size of the output volume. The convolution output, or feature map, retains the spatial connection between pixels by learning image features in small squares of input data. Each element in this output feature map depends on a few input elements, effectively encapsulating local dependencies in our data. After our convolutional layers, we typically insert a pooling layer. The pooling layer acts as a kind of downsampler, reducing the dimensionality of its input while maintaining the most critical information. This scaling back helps to simplify calculations and prevent overfitting. There are two common types of pooling: max pooling and average pooling. Max pooling harnesses the largest value from the kernel-influenced image segment. Alternatively, average pooling uses the average of all values in the pool. Regardless, the pooling operation introduces model invariability for minor translations, rotations, and rescalings. The rectified linear unit, or ReLU, is the preferred activation function in CNNs. This function adds necessary nonlinearity into our model, crucial for discerning intricate patterns. Dropout is occasionally employed after pooling layers to preclude overfitting. This technique randomly sets several layer outputs to 0 during training, providing an excellent method for combining varied network architectures. As variations of convolution exist, we will touch on two: dilated convolution and group convolution. The former uses a filter applied over an area larger than its size due to inserted gaps, while the latter reduces the computational load by splitting input channels into groups and separately applying convolution. Pooling and dropout layers allow us to stack convolutional layers deeper into the network structure without the risk of overfitting. Each successive layer has a larger receptive field, giving it a broader view of the input and therefore aiding in learning higher-level features. Wrapping up, we see convolution and pooling as essential aspects of any CNN. They form the basis of effective feature extraction and downsampling, providing the necessary foundation for a robust and versatile deep learning model. In our next exciting lecture, we'll discuss fully connected layers in CNNs and delve into practical applications of these models across diverse fields like medical imaging and self-driving cars. Keep learning and stay curious, folks.